Welcome to next lesson in magnetic fields in matter. Here in this chapter we will discuss about the auxiliary field H. The auxiliary field H is a more useful quantity than the conventional magnetic field B, especially in the case of magnetic field inside matter. First of all, we will rewrite the Ampere's law in a more suitable form in the case of magnetized materials. Now, the effect of magnetization in a material is to produce the bound current densities. There are surface bound current density and volume bound current density. So, the total field inside a magnetized material is partly due to the bound currents and partly due to everything else. Everything else means the magnetic field is always produced by currents. So, the currents that are not included in the bound currents can be called as free currents. The term free current simply implies that the charge can flow throughout the material without being localized to any atom. So, the current passing through a conventional conductor is a free current. So, in the case of a magnetized material, for example, when current is passing through an iron rod, there will be free current, and at the same time iron is a ferromagnetic material, so there will be magnetization, and then magnetization produces bound currents. So, in a magnetized materials, there will be two types of current densities, bound current density and free current density. So, the total current density can be written as Jb plus Jf. Therefore, the Ampere's law becomes del cross B equal to mu 0 J, which will be equal to mu 0 into Jb plus Jf. So, we can write it as 1 by mu 0 into del cross B equal to Jf plus Jb. Now, Jb is the volume bound current density. In the last class, we have seen that it will be equal to del cross M, where M is the magnetization of the material. So, this equation can be written as del cross of B by mu 0. Because mu 0 is a constant, we can take it inside the brackets, which will be equal to Jf plus del cross M. Now, taking the curls to the same side, we get del cross of B by mu 0 minus M is equal to Jf. Now, we are going to define a new quantity, that is the quantity inside the bracket B by mu 0 minus M. This is defined as a field H, that is H is equal to B by mu 0 minus M, or the magnetic field B equal to mu 0 into H plus M. Now, this new quantity H is called the H field as seen in Griffith textbook, and in some other textbooks this can be called as auxiliary field. Yet another textbook it can be shown as the magnetizing field. So, we will treat it as H field or auxiliary field, and in some textbooks this H will be taken as the magnetic field. So, you need not confuse about it. You take B as the magnetic field and H as the auxiliary field or simply H field. Now, the unit of magnetic field B is Tesla, but the unit of auxiliary field H will be the same as the unit of magnetization M. Both of them have the same unit, Ampere per meter. They are vector quantities. So, our result becomes, that is del cross of B by mu 0 minus M is equal to Jf. Therefore, this B by mu 0 minus M can be called as H. Therefore, this result becomes del cross H is equal to Jf. Del cross H is equal to Jf. That is some equation number 1. Now, integrating this expression over a surface, we get del cross H dot dA is equal to surface integral Jf dot dA. Now, using the curl theorem, surface integral del cross H dot dA can be written as closed line integral H dot dl. And here Jf dot dA represents the free current passing through an area dA. And surface integral of that quantity represents the free current passing through the entire surface or through the Amperian loop here, because that's the boundary of that surface is given by the Amperian loop. So this quantity is the free current enclosed by the Amperian loop, or it can be written as IF enclosed, that is free current enclosed by the Amperian loop. So equation 1 is the Ampere's law in differential form, and equation 2 is the Ampere's law in integral form. It is more suitable in the case of materials, that is, these are called Ampere's law inside materials. And what is the advantage of this Ampere's law? Now, rewriting Ampere's law in terms of H is more advantageous because H expresses the Ampere's law in terms of free currents alone. The peculiarity of free current is we can control the free current directly, but bound currents cannot be controlled by us directly because the bound current depends on the free current as well as on the nature of the material, whether it is paramagnetic, diamagnetic or ferromagnetic, and what is the magnetic permeability of that material. So bound current is a complex quantity, it depends on the magnetic property of the material. But free current is the conventional current that can be controlled very easily by us directly. So the Ampere's law, when written in terms of the auxiliary field H, it contains explicitly only the free current. So if symmetry permits, we can calculate the auxiliary field H immediately by using the integral form of the equation, that is closed line integral H dot dl is equal to IF enclosed. By using this integral form, H can be readily calculated if we know the conventional or the free current and if symmetry permits. So if symmetry permits, H can be found only by knowing the free current. But if there is no symmetry, we cannot find the H simply by knowing the free current. Then we will have to know the free current and bound current. So in magnetostatics, this H plays the same role as the electric displacement in electrostatics. Because in magnetostatics, del cross H is equal to Jf, and in electrostatics, it is del dot D equal to rho F. In magnetostatics, it is closed line integral H dot dl is equal to IF enclosed. In electrostatics, it is closed surface integral D dot dA is equal to QF enclosed. So H plays a role in magnetostatics analogous to electric displacement D in electrostatics. But H is more powerful and useful than electric displacement. In the physics lab, you will be hearing more about H than about B, because you can produce a magnetic field by passing a certain amount of current through a coil, and that current can be directly controlled. It can be directly measured by using a simple ammeter. So from that free current you can determine the magnetizing field H. But determination of the magnetic field is a very difficult task, because the magnetic field depends on the nature of the core which is used inside that coil. For example, if you are passing a current through an infinite solenoid having an iron core, then the magnetic field B will be mu Ni, where mu is the permeability of that iron core. Whereas the auxiliary field will be Ni, small n into I, that is, it depends on the number of turns per unit length and current. That current can be controlled directly by us, irrespective of the nature of the core of the material. We can see that the magnetizing field H will be equal to Ni, but the magnetic field B depends on mu, which will be a complex quantity, especially when ferromagnetic materials are utilized. And also, if ferromagnetic material is used, there is another difficulty, because the magnetic field B depends on the material and also on the history of the material. History means for the same current passing through that coil, the magnetic field will be different because of the history of the material, and it will be discussed later when discussing the ferromagnetic materials. But it is, remember that the calculation of magnetic field B is more complex. H can be calculated if symmetry permits only from the conventional or free current. So H is more popular than B. But in electrostatics, the electric field E is more popular than electric displacement D. Actually, inside the laboratory, we will be speaking about electric field, and we will never speak about electric displacement, because an electric field can be easily set up by applying a potential difference between the plates of a parallel plate capacitor. So that potential difference can be easily measured by using a voltmeter. So you can control the potential difference very easily, so you can control the electric field very easily. But the electric displacement depends on the nature of that material, because the potential is the factor that you can control directly. You cannot take the individual charges, and you cannot measure the individual charges and paste that charges on the plates of the capacitor. It is very difficult, but you can change the potential very easily. So as we can change the potential very easily, electric field is more popular than electric displacement. But in the case of magnetism, we can change the current very easily. So magnetic auxiliary field H is more popular than magnetic field B. So please try to answer what is H field, give its unit in terms of B and M, write down the Ampere's law inside matter in differential and integral forms, give the advantage of rewriting Ampere's law in terms of H in the case of matter, give the unit of H. H is a more useful and popular quantity than electric displacement D. Explain why electric field is more useful than electric displacement in electrostatics. Thank you for watching this video.